Hi everyone, welcome back to Multilingual Natural Language Processing. And today we start the next part of the course in which we go deeper into individual topics in multilingual NLP. And we will talk about morphosyntax. And we talk about morphosyntax because the same meaning can be grammaticalized in different ways in different languages. For example, some languages will grammaticalize the meaning of future as word, others as morpheme, and others as grammatical structure. And today we will talk about morphology, morphological processing, morphological analysis, and inflection generation. And in the next class, we will talk about syntax. We'll start with a reminder from the beginning of the course when we discussed linguistic typology. We have discussed earlier the definition of a word. What is a word is a slippery topic. And we have agreed on the following definition, that words are the building blocks of phrases and sentences that are members in a syntactic category. So they have a part of speech, that words tend to be able to move around relatively to each other and be composed into sentences. So until now, what I mentioned is a syntactic definition. And words are linguistic units that usually have main stress, sometimes as secondary stress. This is a phonological definition. And they can correspond to a unit of meaning. This is a semantic definition. So all this together is a definition of a word which works rather robustly, although there are still some problems, for example, related to idioms and multi-word expressions, such as an expression by and large. Now, words themselves are not atoms, they have internal structure. And morphology is the study of the formation and internal structure of words. As you can see in this drawing, a fundamental concept in morphology is that of morpheme. Morpheme is a minimal pairing of form and meaning. By form, we mean the sequence of sounds, like on the bottom of this drawing, tree. And it can be a sequence of letters, for example, a spelling of the word tree. And this is a mapping between the here the phonetic string tree and the meaning or content of the word. And this mapping is a morpheme. And we say that morpheme is a minimal pairing because we require that morpheme is a pairing that cannot be reduced to smaller subunits. So for example, the plural form of the word tree, trees, will contain two morphemes, tree and s, plural marker. Okay, so words are made of morphemes. And what I highlighted in a sentence on the top or in the example of rich morphology of English on the bottom is what you can see is different concatenations of morphemes. And there are free morphemes, morphemes that occur independently, for example, the word establish. And there are bound morphemes, those that are attached to other words. So in the word disestablishment, establish is a free morpheme, but the prefix dis and suffix ment are bound morphemes. Words can undergo morphological processes or formal operations. What are these morphological processes? These are, for example, concatenation. It is the most common morphological process. If we concatenate the stem, which is the core of the word, with affixes, which are purely grammatical morphemes, that cannot occur in isolation, this process is called affixation. So in the example, disestablishment, the stem is established, and there are prefix and suffix, dis and ment, and the concatenation of, if you concatenate the prefix and then stem and the suffix both from two sides, this process is called circumfixation. So these are concatenative processes. There are also non-concatenative processes. For example, when we add an infix in the, when we add a morpheme in the middle of a string. And another common type of morphological process is compounding. When rather than concatenating bound morphemes, we concatenate free morphemes. We concatenate several stems, like in the word dishwasher, or in the word skyscraper. So you can see that there are two types of morphological processes, and these morphological, several types of morphological processes, more than two. And these morphological processes can change the meaning of the word, like for example with compounding, or with the modification of establish into disestablish, or they can change the grammatical function. For example, cats turning is a plural form of the word cat, but the meaning has not changed. Here are some examples of interesting languages and their morphologies. Tagalog language is spoken in the Philippines. It illustrates a great many formal morphological processes, including prefixation, suffixation, infixation, and reduplication. So here the singular form is formed with prefix ma, and then the plural form is formed with both prefixation and prefixing reduplication, the infix bu. And you can read more examples of interesting examples in the book that I reference below by Laurie Levin and David Mortensen. This is still a draft, but a very nice draft, Human Languages for Artificial Intelligence. Here are some other interesting examples. Arabic is a Semitic language that uses templatic morphology. In these languages, root consists of two or four consonants. And then morphology is represented by vowels and consonants which are inserted in between the root consonants. So the root and the pattern of specific vowels each function like separate morphemes. So they are combined like beads in a string. And on the bottom, we can see Chinese. So although Chinese has poor inflectional morphology, it has many compound words. And so there are compounding processes. You can see examples below, which I cannot read. Okay, morphological functions. So talking about morphological processes such as concatenation, so compounding only tells us part of a story. Our next question is, what are the functions of these operations? The two broadest functional categories of morphology are derivation and inflection. Derivational morphemes, examples are on the top, are used to create new words. They change meaning. They can result in a new part of speech, but of course not always. For example, the same example, establish and disestablish. And another modification is disestablishment, then when we move from the verb to noun. The second type of morphological function is an important class of morphemes are inflectional morphemes. They used to mark grammatical distinctions like cat. And the suffix s will turn it into a cat, but it does not change the meaning of the word. So how do we formally discuss morphological properties of a language and learn about language's morphology in linguistics? So in linguistics, we introduce interlinear gloss text, IGT. Interlinear gloss text is a standard way to explain the structure and properties of the language via examples. It is described in detail in a document that I link on the top of the slide. And I recommend you read this document if the topic of morphology is interesting to you. And on the bottom, I paste the simplest example of IGT, interlinear gloss text, from the same document. So you can see that there are 3 lines. The top line corresponds to the original source language or object language, which is in our case Indonesian. The third line is a translation of the first line into a meta language, which is typically in linguistic papers, this is English, this is a lingua franca. The second line is the gloss, and it is between the first and the third one. This is line, this is why it's called interlinear. Every token in the second line is written in a meta language, in English, but it is not an English sentence. This is an alignment with tokens in the object language. So you can see that the word they in Jakarta now are aligned with the first line. All tokens are aligned, and this is important. Because this gloss contains information, more complicated examples of this gloss contain information about morphosyntax of the object language, which is Indonesian. And in this example, we can see from this even simple example of IGT, we can see the difference between English and Indonesian. And in particular, how English uses copula verb be, while Indonesian doesn't. And here is another more complicated example of the interlinear gloss text between the morphologically rich Russian, this is our object language, the top line, and the bottom line is a translation of the sentence into English, which is a meta language. And in between, you can see 2 lines representing a little bit different information. This is optional, both variants are possible. These are interlinear gloss text. So the word, the fourth token in the Russian sentence, поехали, is split into 3 morphemes corresponding to stem, past tense, and plural. And you can see this specification in the IGT lines 2 and 3. So this would be a stem, go, and then past tense, and the number, plural. And the word bus, автобусом, its 5th token in Russian, is split into 2 morphemes corresponding to stem and suffix marking the case, instrumental case. So you can see from this linguistic description and alignment between the 2 sentences and the morphological analysis of individual token in the top sentence, how the morphologies of Russian and English are different. And you can see that morphology of Russian is significantly more complex than the morphology of English. In this slide, which I will not read to you, but you can use it later as a reference, I list the types of morphological categories across parts of speech. All languages possess the same set of about 25 categories, number, gender, tense, each of which have several functions. So there are roughly 25 categories and roughly 100 functions. For example, a category for nouns, a category number of the object can be singular, plural, or dual across different languages. This corresponds to number. Another example of a category is noun class, which noun classes are linked to grammatical gender in Indo-European languages, but in other languages, this can be arbitrary set of categories. And all nouns must belong to a category. So an interesting example of noun classes is in Swahili, which is an African Bantu language. There are several classes. I don't remember, I think it's 7. There is a class corresponding to animate nouns, denoting people, animals, insects, birds, fish. There is a different class corresponding to trees, plants, body parts, and another class corresponding to foods, and so on. And there is a separate class for singular animate nouns versus plural animate nouns. So these are semantic classes, and the different morphological rules, different prefixes and suffixes are applied to different classes. So languages differ in how they express these categories. Some use lexemes, like Chinese, Vietnamese. These are morphologically what we call poor languages. Some use freestanding grammatical morphemes, such as pronouns, prepositions, so which means that they express the same categories but through syntax. And some languages use affixes, prefixes, suffixes, and this means that they express these categories through morphology. So this is what it means when I said in the beginning of the class that different languages grammaticalize these relationships and the categories and functions differently through words or through syntax or through morphology. And this is why we have different types of languages which we categorize into morphological typology. So there is also a disagreement on the typology, but I present an analysis from David Mortensen's and Laurie Levin's book. And traditionally, languages have been divided into 4 types based on how morphologically rich they are. Languages like Chinese, Vietnamese, and a little less English are called isolating or analytic languages. These languages have relatively little morphology and very little inflectional morphology, with the exception of compounding, like I showed in the example of Chinese. So most words consist of a single free morpheme. Languages that, similarly to isolating languages, have relatively few free morphemes per word, but unlike isolating languages, have many prefixes and suffixes, are called fusional or flexional languages. Examples include Greek, Russian, German. There is a special subclass of fusional languages, which are called templatic languages, as I showed in previous example. Arabic and Hebrew is also like this. The next category is agglutinative or agglutinating languages. These languages often have many morphemes within a word. Examples include Finnish, Turkish, and Swahili. And these languages have very long words. And finally, the most morphologically rich languages are polysynthetic, which can include the whole sentences, whole propositions. They can concatenate them into a single topic. So analytic languages have lower morpheme to word ratio and higher restrictions of word order in a sentence. And languages with richer morphology, synthetic languages, typically have higher morpheme to word ratio and more free word order. There are type token curves that also can visualize how properties of morphologically rich languages. So we can see that the richer the morphology of a language, the higher is type to token ratio in a language. And consequently, the higher is the sparsity of tokens in the corpus. Here, for example, this paper by Setola et al. 2012, they took a multi-parallel corpus consisting of 6 languages with varying degrees of morphological complexity. So these are the same sentences. This is a multi-parallel corpus, but written in different languages, in English, Chinese, German, Arabic, Turkish, and Korean. And you can see that as the morphological complexity of the language increases, the number of types in the corpus increases, resulting in a steeper curve. The most morphologically rich in this drawing is Inuktitut, which is a polysynthetic language. It concatenates many morphemes together into single words, and on top of this, it has complex morphophonological processes between morphemes. So for Inuktitut, at 1 million tokens, it has approximately 225,000 types, compared to English, which is for around 1 million tokens, has only 30,000 types. Okay, so due to morphological complexity and the diversity of languages, there are several challenges in processing morphologically rich languages. First is related to high lexical sparsity due to the variability of morphological forms. This leads to sparse statistics. Many forms of words appear only once or few times, even in very large corpus. And there are many plausible word forms that do not appear at all. These are called out of vocabulary words, or OVs. And these out of vocabulary or rare words that appear only once or twice lead to errors in systems such as machine translation, speech recognition, dialogue, question answering, and so on. So this is the first challenge of processing morphologically rich languages. The corpora, no matter how large they are very sparse. But on top of this, morphologically rich languages are often resource poor. So the problem of sparsity is much more acute, specifically for these languages. An additional challenge of morphologically rich languages is their complex word agreement. This leads to agreement errors in language generation, especially when we need to model agreement between words that appear far from each other in a sentence. Just because, as I mentioned in in a few slides before, that morphologically rich sentences languages also have more free word order. Okay, so on top of this high variability, there is also a mismatch between morphologies, or variability between morphologies across languages and language families. And this is, so mapping between morphologies of different languages is difficult. This leads to difficulties in transfer learning. When we want to transfer training corpora from one language to another, this can lead to problems. This can also lead problems in translation errors. For example, when we translate from languages that don't have the concept of definiteness, like Chinese or Russian, and so Chinese and Russian don't have definite and indefinite articles, and when we would like to translate from Chinese or Russian into English that have definite and indefinite articles, so these translations tend to contain errors. And another problem is that differences in mapping across morphologies of different languages can lead to exacerbation or amplification of social biases. For example, when we translate from languages like Turkish or Hungarian that do not mark gender of third-person pronouns, like he or she, and we translate from Turkish or Hungarian into English. So it was shown in previous work that, for example, translation of lower status occupation would be translated with female pronouns, whereas the translations of higher status occupations would be translated with male pronouns. So a Turkish sentence that is written basically, they are a nurse, would be translated as she is a nurse, and they are a scientist would be translated as he is a scientist. And this just amplifies biases in English training data. So to summarize, main challenges for processing morphologically rich languages are high sparsity, different errors in generation, for example, caused by the need to enforce agreement between words, and the differences in morphological properties across languages that are different to map across languages. And because of these challenges, we do morphological processing and incorporate morphological knowledge into models explicitly. So what are the types of morphological processing? First, morphological analysis, and we can talk about morphological parsing or morphological segmentation. The second is related to generation, and the task can be inflection generation or full paradigm completion. I will show later an example. And the third, less common task would be an acquisition of morphology. Although we have resources for hundreds of languages where we know their morphology, thousands of languages, we still don't have enough knowledge about their morphological properties. So the task of acquisition of morphology would focus on learning languages' morphologies automatically. So the most common task is morphological analysis. And also it is called morphological parsing. Our input is a word and our output is a word stem and features expressed by other morphemes. For example, given an input cats, morphological analyzer's output will be cat plus n, which corresponds to noun, plus PL, which corresponds to the plural form. So morphological parsing is the process of determining what are those morphemes given an input word. As you can see in these examples, this information, morphological information, comes from three major sources. First, from lexicon. So we need to know the stem. Second, from morphotactics, we need to know morphosyntactic rules. And third is from spelling or pronunciation rules, because we need to know, for example, the word cities, we need to know that a stem city, which ends with a Y, in a plural form will be changed into cities with I. Having this information about lexicon, about morphotactic rules, and about spelling rules, we can build a morphological analyzer. Classical approaches to morphological analysis used finite state transducers. And they achieved high accuracies, high results, good results. So in these approaches, we have two types. Lexical and surface, as in this example, in the drawing on the top. These drawings are from the Jurovsky and Martin textbook. So, and we build a finite state transducer. So either one, so it can be inverted. So either lexical form can be an input, surface form can be an input, and the output can be stem plus morphological analysis. Or a stem plus morphological analysis can be an input, and the output would be a surface form. So we will build the transducers that, given an input word cats, it would read the word, the input letter C and output C, read A, output A, read T, output T, then read plus N and would output an empty string epsilon, and then it would read plus PL plural and would output S. So the output would be cats, and it's coming from lexical interpretation to the surface interpretation. So on the bottom, we have a simplified FST for morphological parsing. Cats goes from Q0 to Q1, from state Q0 to state Q1. This is a regular noun. Then Q1 outputs an epsilon for the noun plus n. And then we can go from Q4 to output S, a plural form, and we have the end of string in Q7. So we can build such an FST, finite state transducer, as a recognizer, and it would say, is it a legal string if we accept it, and or if it's not a legal string, if it's not a word, a legal word in a language. In this case, the FST would reject it. And we can build this FST as a translator, in which we input a string of characters from the surface form and output the string of morphemes. Okay, so in 2016, there were a surge of papers that started to replace finite state transducers with recurrent neural networks. So this is one of the many examples of papers that I present here by Katarina Kahn and her collaborators, Ryan Cotterell and Henrik Schutze. They showed how to implement the same task of morphological analysis using recurrent neural networks. And I present specifically this paper because it's interesting for two reasons. First, they show how to do canonical segmentation rather than surface level segmentation of words. So canonical segmentation, so you can see in this example for the word achievability, how would, for the input achievability, how would an output surface segmentation look like, and how would output canonical segmentation look like? So for a surface segmentation, we would just segment the input sequence into substrings. In canonical segmentation, we don't only segment the sequences into substrings, but also replace substrings with the canonical form. This canonical segmentation has several representational advantages because it shows morphemes that are not obfuscated by morphology. So it reduces the sparsity more significantly. But it is also more challenging. For example, it would be difficult to implement with finite state transducers because it doesn't only segment words into substrings, but also reverses orthographic changes. So how did they do it? They first used the standard character-based bidirectional GRU encoder with attention. And then they have a unidirectional GRU decoder. So this is a very standard sequence-to-sequence architecture, RNN with attention. And then a novel component they introduced was neural re-ranking for segments to identify canonical segments. So in particular, when they kind of produce the segmentation of a word, they first output a surface level segmentation, but then they did re-ranking and specifically looked for segments that are more frequent when they occur as an independent word in a lexicon. And for this, they incorporated simple lexical information into word embeddings that added an additional dimension to the word embedding, a binary feature that said whether this word appears as an independent word in the lexicon or not. So this is a standard sequence-to-sequence character-based model plus a re-ranker on top of it to prioritize words that appear more frequently as independent words in the lexicon. So in this case, in the segmentation of a word achievability, the word, so the second token, able, would appear more frequently than the token ABIL. So how do we evaluate morphological analysis? There are several evaluation measures that are described in the paper, in the previous slide and in several other papers. First is error rate, defined as 1 minus the proportion of guesses that are completely correct. So proportion of 1 minus proportion of outputs of the models that are completely correct. Second is edit distance. So when the first is a hard measure, it's either correct or incorrect output. The Levenshtein distance would measure the similarity between the guess and the gold standard form. And finally, morpheme F1 score calculates the precision and recall of correctly generated morphemes. Where the training corpora usually come from in this paper and other papers on morphological analysis. A most common resource to work with is Unimorph. It annotates hundreds of languages using a unified schema. It includes currently annotations for 110 languages. And I put the link in the slide. Okay, so this was about morphological analysis. The second type of prominent type of direction of research is focusing on morphological generation. In particular, inflection generation. There are two tasks. One is to generate a single inflection. So our input would be a lemma and grammatical features. For example, this is an example in German. Calf, which is calf, and the grammatical features such as case, nominative, and number plural. Inflection generator will output Calber. And the second task, which is a generalization of inflection generation task, introduced relatively recently in Sigmorphone competitions, that given a lemma as an input, we would need to fill a table. And this table, this means we need to generate all possible inflections of a word for all morphological categories. So an example where inflection generation, either inflection generation or paradigm completion is useful is for reducing sparsity of the corpus. For example, in machine translation suffers from data sparsity, as I mentioned before, when translated in morphologically rich languages, since every surface form is considered, every token is considered as an independent entity. And to alleviate the problem of sparsity, we can translate into lemmas in the target language and then apply inflection generation as a post-processing step. So these tasks, morphological analysis, morphological inflection generation, paradigm completion, they are widely explored, in particular in Sigmorphone competitions. So Sigmorphone is a special interest group on computational morphology and phonology, and they organize workshops and share tasks every language. And I put here some interesting summaries of workshop tasks that you can look into. And there is a lot of research, so I really gave a high-level overview. Morphological inflection generation, in general, the base model is usually a simple bi-LSTM with attention, so recurrent sequence-to-sequence model. And then, while the base model is simple, there are several interesting challenges specific to morphology. An interesting challenge, for example, is how to enforce monotonic alignment between input and output, because we, unlike in machine translation and morphology, we don't need to do a lot of reordering to the output sequence. Second interesting challenge is how to better learn longer distance relationships between characters to model variation in inflection due to spelling and phonological rules in a language. So some of the papers focusing on shared tasks specifically focus on, for example, adding a CRF layer on top of the decoder to better model relationships between characters in the outputs. And if you want to know more about the field, you can start with the Sigmorphone 2020 shared task summary, which provides an overview and the kind of historical development of the task and the links to interesting papers. And to read a particularly interesting paper about morphological generation, let's read this paper that I put in this slide. So it particularly focuses on low resource settings. So morphological inflection has been pretty thoroughly studied in monolingual high resource setting. But in this paper, Adonis and Graham focus on low resource perspective and on cross-lingual transfer across languages. And your task for the discussion is just to read this paper and provide your insights. For example, you can provide a critique about an individual component of the model. So the model in the paper consists of several different components. So you can talk about an individual component or individual experiment or experimental setup. And in particular, you can propose ideas for follow-up work, or how a specific modeling decision could be adapted to a language of your choice. For example, a language that you speak. And that's it. Thank you and see you tomorrow.